All righty, let's get started. So we're going to continue our discussion of optics that we started last time. Let's see, what did we have? A few relationships or equations for light and optics. We know that the first big one is a relationship between the velocity of a wave, the frequency of the wave, and the wavelength. So v is velocity. Of course, every wave moves at a certain speed, and that speed depends, of course, on what the wave is moving through. So if we talk about sound, for instance, when you speak or when you make any noise, any sound that's created, those sound waves, the pressure waves, move through the air at a certain speed. And in fact, the speed is about 343 meters per second. But of course, sound can travel in all sorts of materials. It doesn't have to travel in the air. You can have in the water. For instance, when, especially back in the Cold War days, when submarines were always hunting each other and they would use sonar and the like, they had to take into account the fact that sound travels faster in water than it does in air. And same is true for any wave. The waves that travel through a string, for instance, like a guitar string or something like that, that wave will travel through the string at a certain speed, and that speed depends not only on the material of the string, what's it made of, but also the tension of the string. So if you tighten the string, that is when you're playing at a guitar and you go to tune it, you tighten or loosen the strings, that's changing the speed at which the wave travels through the string. And that, of course, changes the frequency of the sound. So all waves have certain speed, but that speed depends on the material. So when we say the speed of sound is 343 meters per second, that's only in the air. The speed of sound in water is a different speed. And that's true for everything, light included, of course. F is called the frequency. And the frequency means how many times the wave oscillates per second. So every wave is oscillating. That's the waviness of the wave. And the oscillation, the amount of times it moves up and down per second, let's say, is called the frequency. And then the wavelength kind of combines these two characteristics and says, how far does a wave travel in completing one oscillation? So as the wave is moving along, let's say left to right, and it's oscillating up and down, well, it's going to travel a certain distance in the time it takes for the wave to travel, to oscillate one complete time. And that's what's called the wavelength. And so this equation relates to the three characteristics of the wave. Another equation we know is that the period of a wave, capital T, is just 1 over the frequency. So this is sometimes more useful to talk about the period rather than the frequency, but they're pretty much the same thing. The period means how long does it take, how many seconds does it take to complete one revolution or one oscillation. So very similar to a frequency. The frequency is how many oscillations in 1 second. The period is how many seconds for one oscillation. They're inverses of each other. And then we had the big equation, the mathematical equation of a wave, and it says y is equal to a, which is the maximum amplitude. How big is the wave at its maximum, times the sine of kx minus omega t. And here, k is defined as 2 pi over lambda, and omega is 2 pi times frequency. And so this equation is the equation which defines a wave. Doesn't matter what wave we're talking about. It could be water waves in the ocean. It could be waves in a string. It could be sound waves. It could be light waves, whatever. This equation can predict for you or help you predict the height of a wave if you're looking at a certain position at a certain place at a certain time. And so what you would do if you were going to use this type of equation, you would be telling the equation the x and the t. Okay, those are the things you tell it. You say, I want to know about the wave at this point at this time. The other variables are the things that are about the wave. A, the maximum amplitude. How big does the wave get? You can't tell it that. The wave tells you that. K, the thing that talks about the wavelength. It's called the wave number, 2 pi over lambda, but lambda, of course, being the wavelength. That's something the wave tells you. You don't know, you don't make it up. The wave is what it is, and so you get that information from the wave. And of course, omega, called the angular frequency. Again, that comes from the wave. But this equation is a nice equation to be able to make predictions or whatever, to know as much as possible about a wave. And so we want to do some examples of the types of calculations we may see when we need to work with light waves specifically, or waves more generally. So let's do a few examples. Let's see, the first example, we could say a wave traveling with a velocity of 1,000 meters per second has a period of 0.02 seconds. Okay. Part A, calculate the frequency of the wave, and then part B, calculate the wavelength. So there's our question. We have a wave. We know some things about it. We know how fast it travels. First of all, it travels at 1,000 meters per second. So I automatically know this isn't light, because we know the speed of light is 3 times 10 to the 8th, at least in the vacuum. And this is much, much, much slower. So this is something more closer to, you know, waves on a string or sound waves in a certain material, things like that. But regardless, we have some wave, we know how fast it moves, and we know its period. So the first question, calculate the frequency of this wave. Well, we know that a relationship between frequency and period. Of course, period is 1 over the frequency. We want the frequency, so to solve this equation, of course, for frequency, and we get frequency as 1 over the period. So plug the numbers in. Remember our units. Units are important here and always in physics. Units of frequency, 1 over seconds. Units of period, seconds. Units of wavelength, meters, things like this. So when we want the period, we better have the period in seconds. And indeed we do. So 1 over 0.02. Plug that in our calculator. And we get an answer of 50 hertz. All right, so not so bad. Let me make sure that's clear. 50. Given the period, we want the frequency. Very easy. Just take the inverse. 1 over the period gives you the frequency. Now the wavelength. what are we given? We're given the speed of a wave, we're given the period, and now we know the frequency. And what we'd like is the wavelength. So looking at the possible equations we have to work with, of course, the first equation, which relates speed, frequency, and wavelength, will be the equation we want to use here. So we say V is frequency times lambda. I'm looking for lambda, I'm looking for the wavelength. So lambda is velocity over frequency. Plugging our numbers in, we have 1,000 for the velocity. Of course, it's meters per second. Make sure you have the right units. Over frequency, we just figured out is 50. And so what is that? 100 over 5, which is 20 meters. And there we go. This wave, whatever it is, moves with a velocity of 1,000 meters per second, has a frequency of 50 hertz, and a wavelength of 20 meters. All right, any questions about this problem? Any questions about this example? All right, well, let's try another problem then. Example 2. Let's say a particular beam of light has a wavelength of 20 nanometers. Okay. A, what is its wavelength? I'm sorry, not wavelength, wave number. And B, what is its frequency? Okay. So here we have a beam of light. So we know what kind of wave we have. We have a light wave. And we know about its wavelength. It's 20 nanometers. Okay, and what we'd like to find is the wave number of this wave and its frequency. So starting with the wave number, the equation K, wave number, is 2 pi over L. I mean, lambda, not L. So pretty straightforward. All we need is the wavelength. We know the wavelength is 20 nanometers, so we plug in the numbers, 2 pi over lambda. However, we have to be careful here. Remember, units are important. We need meters for wavelength. We've given nanometers here, so we have to convert. And if you remember, nanometers is 10 to the minus 9 meters. So 20 times 10 to the minus 9. All right, so get out our calculator, 2 pi divided by 20 times 10 to the minus 9. And I get 3.14, of course, times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And the units, we could call it 1 over meters for units. So wave number, very easy if you know the wavelength, of course, because it's just 2 pi over the wavelength. Here, one of the issues is the units that were given for wavelength are not in meters, so we have to convert to meters. But that's not a big deal. Nanometers is 10 to the minus 9. Remember, micrometers or micrometers is 10 to the minus 6. Picometers, 10 to the minus 12. If you remember your unit conversions, converting nanometers is 10 to the minus 9. So plug the numbers in and we get an answer. Now I put mine in scientific notation. Of course, if we didn't, it'd be 314159265.4. Okay, but that's messy looking. Usually as a scientist, when you have big numbers, you're generally going to put it in a scientific notation, especially because when you're doing actual research, you care about things like significant digits. And so it doesn't make sense to keep all the digits. You're going to be rounding at some point. And so that's why I do scientific notation. That's a secondary reason I do scientific notation. Primary is it's just cleaner to look at. Now, part B, we want the frequency. Now, here we have a bit of an issue. We want frequency, and what do we know? What we know is the wavelength and the wave number. So if I look at the equations I have, can anybody tell me how you would calculate frequency given you know wavelength, or given you know the information in this problem? Anybody have any ideas? How do I calculate frequency? Any ideas, or is everybody still asleep? All right, well, yeah.
Would you divide the wavelength by the wave number?
Well, let's see what would happen. What would happen if I do that, just as an interesting thing? Divide the wavelength by the wave number. Well, wavelength is lambda. Wave number is 2 pi over lambda. So to divide these, I would get something that is lambda squared over 2 pi. Okay. That's really nothing that I know of. Yeah, I can't think of anything that this would be called. So no, that can't do it. Any other ideas? I can give a hint. Hint is what I'd like to do. If you look, really the only thing other than period that has frequency in it is the first equation, and that says velocity is frequency times lambda. This is what I'd like to use. However, if you notice, it seems I only have lambda and I want frequency. So what can I do about this third variable, velocity?
Use a different equation to solve the velocity.
Okay.
With the given information that we have. So
we don't have it, like one of these light equations doesn't have velocity in it. So if we were to try to do that, then we'd have to pull something from physics. And so we have things like meters, you know, a distance over time, how far does it go and how long does it take? But we don't have that information either. What else? What other ideas do we have? I want frequency. I know lambda. But in order to calculate frequency, I need velocity. Is there any information in the problem that would help me that I didn't see before?
we know what the wavelength is. Wavelength is 20 nanometers.
That's true. And that would be
And then
lambda, which is one of the things we need. That's perfect. But we still need V. How do we get V?
oh, it's light. So it's the speed of light. Oh,
perfect,
okay.
perfect,
Oh.
perfect. Exactly
Okay.
right.
That's,
Hidden
yeah.
in the problem is the fact that we do know the velocity for this wave because I told you it's light specifically. The previous example, I don't tell you what kind of wave this is, so I had to tell you the velocity. But this problem, just the fact that I say this is light, is kind of like when we're doing first semester physics and we're doing some kinematic stuff, and I say you throw a rock off a cliff, even though I don't tell you in the problem, you know the acceleration is due to gravity, and gravity is 9.8. You just know it, even though the problem doesn't say it. Here, the same thing. Because I tell you light, that tells you immediately you already know V has to be 3 times 10 to the 8th meters per second. Now, of course, if we're talking about in water or something else, then this is a different number. But that's just more complicated than we're going to worry about. So actually, the problem told us that second piece of information, even though it doesn't look like it. So now we have it. Solve for frequency. Frequency is velocity over lambda. Velocity we know is 3 times 10 to the 8th. Lambda we know is 20 nanometers, so 20 times 10 to the minus 9. And now we could plug our numbers in. So 3 times 10 to the 8th over 20 times 10 to the minus 9, and I get 1.5 times 10 to the 16 hertz. Huge, huge frequency, but generally speaking, that's what light is. Light has very high frequencies. So there we go. And now you see why I wanted to do this particular example, because it sets you up. It tells you so that from now on, you know to look for this little trick. When you're reading through a question, we always have a tendency to ignore everything except for numbers. When we see a number, then we make it important. But we have to be careful here, and we should generally be careful, because a lot of times there's information hidden in the text that isn't very apparent. And here, the fact that we're talking about light implies we know the velocity of this wave is a particular number, and so we have to be aware of that. So very good. Any questions about this example? Once we know, then it's pretty easy, right? The actual equations are very short. They're small equations. They're easy to handle. The issue with this type of stuff is knowing the information you need to know to use the equations. And now that you see an example like this where there's hidden information and you know to look for it on a test or on a homework problem, if you see that this is light, make a note, either write it on the side or whatever you want to do to remember, okay, whether I need to know it or not, I know the velocity of this wave is a particular number. Now let's do another example. This one will be, let's try this example. Write down the functional form. That also means the mathematical equation, okay? Functional form, mathematical equation means the same thing. Write down a functional form of a wave whose velocity is 1,000 meters per second and whose period is 0.05 seconds. Assume the max amplitude is 2 meters. All right. So here we have a question, and we're talking about a wave, but what we want is the big wave equation, okay, the equation which defines waves. And when I say that, what I mean is y is equal to a sine kx minus omega t. That's what I want. I want to write that down for this particular wave. So in order to do it, the things I need to know, of course, are the maximum amplitude. I need to know the wave number, and I need to know the angular frequency. Okay. X and T, remember, those are variables. Those are the things that you would insert into the equation when you want to get a number from something. So you leave those as X and T. But K, omega, and A, those are the things we need. So our job is to try to figure out what these variables are. First of all, we know A, okay? Maximum amplitude is 2 meters. We know that already. That's no big deal. The other two, of course, are the things we need. So before we do it, of course, let's write down what we know. What we know is the velocity of the wave is 1,000. So V is 1,000. And we know the period is 0.05. So capital T is 0.05. What we want is K, which of course is 2 pi over lambda, and omega, which is 2 pi times F. So that's our job. Our job is take this information and calculate what K is and calculate what omega is. So if we start thinking, I know period. Period is really close to frequency, right? So let me work on that first. Period is 1 over the frequency. So I could use this to say frequency is 1 over the period. 1 over the period, 1 over 0.05. And I get 20 hertz for the frequency. But I don't want frequency. What I want is omega. I want angular frequency. So I take this and I say omega is 2 pi times frequency. And I just figured out what frequency is. So 2 pi times 20, which is 40 times pi. Now, here's the thing for these problems. You can either leave it like this, 40 pi, because it's a little cleaner to look at, or you could actually plug 40 times pi into your calculator and get an actual answer, like a decimal answer, I should say. Either way is fine on a test. I'm going to leave it as 40 pi just because it looks nicer. Okay. So omega is 40 times pi. There we go. I know one of them now. That's done. Now K is the other thing I want. K is 2 pi over lambda. So what I need is lambda. If I need lambda, what do I know? I know the velocity, I know the period, I know the frequency, and I know the angular frequency now. So likely what I'm going to do is, in order to get lambda, I'm going to use velocity as frequency times lambda. Solve this for lambda. Velocity over frequency. Velocity I know is 1,000. Frequency I calculated over there. That's 20. So 1,000 over 20 is 50, I believe, 50 meters. But now that I have lambda, remember what I want is K. So K is 2 pi over lambda. So I have 2 pi over 50, which is pi over 25. And again, you could either leave it like this fraction with pi in it, or you could plug this into your calculator to get a decimal. Either way is perfectly fine. I'm going to leave it like this just because decimal is going to look a little messy. But again, if this were a test and you actually plug this into your calculator, got a decimal, and you use that, I would know that that's the answer as well. So don't feel like you have to leave fractions like this. But okay, now I know omega, now I know K, and I already knew maximum amplitude, A, from the problem. So now I have everything I need. Just plug it in. Why? is equal to A, and A, if you remember, was 2 meters, times sine of K. K, I just found out, is pi over 25, times X, minus omega, and omega is 40 pi times T. And there we go. There's the functional form. This equation, this function, defines this particular wave that I have, written down as a problem mathematically. And thus, if you know all of this information, you know everything you need to know about the wave. And you can then predict. You could say, okay, if I wait 10 seconds and I look over here, where will the wave be? How high what will be the amplitude of the wave, basically? So, any questions about this style of problem? You're given a wave, some piece of information, and you want to write down the big wave equation for him. You need the 3 pieces of information: amplitude, wave number, angular frequency. So you use whatever methods you can, whatever equations or relationships you know, to get those 3 pieces of information. You plug them in, and you're left with a formula or an equation or a function that looks something like this. So any questions? All right, well, with these examples, if you can handle these types of examples, these also on Canvas are the practice problems with this type of stuff and the solutions to them. So you'll see more problems that you could work on at home to practice them, but they're all like this. There's some combination of frequency, wavelength, period, velocity, all that kind of stuff. And it's just a matter of, given some things, can you calculate the other things from them? These are the equations up here, the relationships we need to know. And with all these relationships, we can then handle any of these types of problems. Now, what I want to do today for the rest of the day is talk about a different characteristic of light, specifically light now, that is not covered with these characteristics. Okay, so all waves have a frequency and a wavelength and a velocity, a period, a wave number, angular frequency, all of that stuff. All waves have it. Now we're going to transition to purely light. Light has another characteristic. And the thing about this characteristic is our eyes cannot see it. So this particular characteristic, if we're looking at 2 different sources of light, and one light has this thing for a characteristic, the other light has this other characteristic or a different version of it, our eyes can't tell the difference. However, there is a difference, and other equipment, cameras, and we can design equipment that can see the difference. And thus it's important. And what this characteristic is called is the polarization. Polarization. So light has a polarization. Now, what is polarization? Of course, it is defined as the direction of oscillation of the electric field. So if you remember what light looks like, as it moves from left to right, it's a wave. The electric field waves in some direction, let's say up and down in this case. And then there's also the magnetic field, which is perpendicular to it, and it waves too. In this case, it waves back and forth. And that whole set of things moving from left to right in this case, is what's called light, electromagnetic radiation, an electric field oscillating and a magnetic field oscillating together as they move. Their oscillations are always perpendicular to each other, and that those two perpendicular directions are also perpendicular to the direction of motion. So we call it a transverse wave. And so, of course, I don't have to draw the light with the black, the electric field part. So I'll label it, electric field is the black one, and the magnetic field, let's say, is the green one. I don't have to draw it where the electric field is oscillating up and down. The electric field can oscillate back and forth, and the magnetic field is up and down. Or the electric field can be oscillating left and right, and the light is actually moving from top to bottom. Okay, so of course, this thing can rotate, it can move in any direction it wants. So I draw it like this because it's easier to draw, but it doesn't have to be up and down. So whatever the direction of the electric field's oscillation, in this case, it's up and down, but in other cases, it may be different. That direction is what's called the polarization of that light. And so for us, this particular example, the light is polarized up, or technically up and down vertically. But if you know it's up, then it's also down. If it oscillates up and down and we say it's polarized upwards, you know it's also downwards too. So that's the symbol. Very easy. The way I'm going to do this symbolically is when I say you have light that's polarized upwards, I just put a little up arrow. And that tells you, okay, the light is polarized up. If the light is polarized to the right or left and right horizontally, then I'll put a little right arrow. And of course, the light can be polarized in any direction at any angle, because the light doesn't have to move in, from left to right. It can be moving, this way or something. And thus the oscillation may be like this. And so you'll have a polarization that's at an angle. All right, so that's what the polarization is. It is purely just the definition of the direction of oscillation for the electric field. Now, we could have defined it as the magnetic field, but whoever invented polarization or first discovered this characteristic defined it as the direction for the electric field. And that's the way it is. Now, why is this important? If our eyes can't see it, then who cares about polarization? Well, it turns out that it actually does have effects. One of the effects is the fact that we can create materials, maybe films or filters or things like this of a particular material, which can allow light to pass or block light depending on if the polarization is in the right direction. So you can have what's called a polarizing filter. Or I'll just shorten it to polarizer. And it is some piece of material, like a piece of thin plastic, a plastic sheet. And what you can imagine, this is not what it is. I'm warning you now, this is not actually what it is, but for a picture in your mind, it's useful to think about it this way. You can imagine that it's got a bunch of like slits. Let's say vertical holes in this case. Slits, very, very thin, extremely thin. And so what this does is it allows only light to pass through it if the oscillation is a vertical oscillation, because then it could fit through the slits, right? If you were to have the oscillations horizontally, then they're too wide to fit through these holes. Just like if you think about, Star Wars movies and you have the Millennium Falcon and it could fit, it's going through a different ship and it fits through the little thin crevice. It has to position itself so that it could fit through that slit, that little hole. Same thing here. the light, the electric field's oscillating in some direction. If those oscillations line up with the slits in this polarizer, then the light can get through. If not, then it blocks it and the light is not allowed to get through. And so what you would have is some amount of light, for a general beam of light coming through. Some amount of light will get through, and that is the amount of light which happens to be polarized in the same direction as the filter. And whatever is not in the same direction is just blocked off. And of course, the filters don't have to have their slits vertical. They could be in any direction. They could be horizontal, they could be at 30 degrees, whatever. And so we could design different filters to only let light through if it's polarized in the correct direction. Now, this is useful because we actually do use it a lot in life. For instance, one of the big places you've probably heard the word polarized before is in polarized sunglasses. And so the way this works is normal sunglasses that are not polarized, what they do is they take plastic and they shade the plastic. They make it dark. And so just by making it dark, when you put them on, everything looks dark, which is good if you're going out into the bright sun. But then if you're inside, that's not so good because it's not so bright inside. So now everything's too dark. But fine, you wear the sunglasses outside, you don't wear it inside, whatever. Polarized sunglasses work differently. They can also be darkened, but one of the main ways that it helps with glare and things like this is the lenses of these polarized sunglasses have their slits, their polarizing filters, have their slits lined up in a particular direction, let's say upwards, vertically, like this particular example. And so when you go outside, the light you're probably trying to block is the light coming from the sun. Well, here's the thing. The sun, when it shines light, that light is what's called unpolarized light. Now, this is a very bad name. I hate this name. Unpolarized. Unpolarized does not mean it's not polarized. That's why this is a bad name. Every light is polarized. It has to be, because polarization is the direction of the electric field. And every piece of light has an oscillating electric field. So it must have a polarization. What unpolarized really means is it means it's randomly polarized. So generally speaking, if you have a source of light, let's say, it shines light and the polarization of that light is always in the same direction. Okay, it's always in the same direction, let's say vertically. The sun, when it shines light, it's shining light that's polarized in all sorts of directions. So one particle of light coming out may be vertically polarized, the next one may be horizontally polarized. And then the next three may be at 30 degrees, and then it's vertical again. So the light coming from the sun is always in different directions, always polarized in different directions. So it's random when you see a piece of light coming from the sun, which direction it'll be polarized. And the name given to this is unpolarized light. But again, it's not unpolarized, it's actually just randomly polarized. So because of that, if you wear polarized sunglasses, the lenses of the glasses have the filters, let's say, polarized vertically. And so what those filters do is it only lets light go through the lenses of the glasses if the light is also vertically polarized. And if it's not vertically polarized, it blocks it. It's a way of thinking about it. It's not quite accurate, but that's basically what's going on. So if you have light that sometimes it's up, sometimes it's horizontally, and you put these sunglasses on, then basically half the light will be blocked. because half the time it's polarized in the right direction, the other half it's polarized in the opposite direction, since it's random. And so the way those sunglasses shade your eyes from the bright light is not because it tints the glasses itself, but rather it just either allows light through or does not allow the light through, depending on its polarization. And so if you have polarized sunglasses, and the only way it actually darkens is by this polarization effect, and you shine light at them that's polarized vertically, then it doesn't block any of the light, and it looks like you're not even wearing sunglasses. But if it happens to be polarized in the opposite direction, let's say horizontally, then you don't see the light at all. It's completely blocked. None of the light gets through. And so it's a different method of blocking light. Instead of just tinting the glasses so everything looks dark, polarized sunglasses block light that's polarized in the wrong direction and allows light in that's polarized in the correct direction. And effectively, what that means is when you go outside, you block 50% of the light and you allow 50% of the light through from the sun. So it blocks a lot of light, but it doesn't darken everything. It only blocks light that's polarized in the wrong direction. Okay, this is one effect. Any questions about this effect so far?
So is it, are we going to need to determine like which, in which way light is polarized?
For our purposes, what we're going to do is the types of problems we're going to do is I'll tell you, you start with light polarized this way, and then here's a filter. You tell me how much light gets through. That's kind of the style of problems we're going to be doing. So you won't have to figure out what the polarization is. You'll be given the polarization. You have to figure out what will make it through and what will be blocked. And there's going to be an equation for this, of course, that we're going to get to. But so no, we won't have to figure out the polarization. We'll be given the polarization, and we have to figure out what's allowed through the filter and what's not. And of course, what if we have two filters, one right after the other? So one filter blocks this much, the next filter blocks this much, what gets through the whole system, that kind of stuff. Now, there's a second effect, by the way, which is important for polarization that almost everybody, but maybe not everybody, has seen or knows about at least. And that is 3D movies. 3D movies, the goggles or the glasses you wear when you're in the movie theater or the IMAX or whatever, make use of this polarizing effect. And this is how they do it. Your eyes, so first of all, we have two eyes. We're not cyclopses. We have two eyes, and our two eyes are separated a little bit on our head. So what that means is when you look at an object, you're seeing the object from two slightly different angles. Okay, now usually this is bad, obviously, because everything would look blurry because you see the same object in slightly two different angles and they overlap each other. But your brain is so powerful that it instantaneously takes the information coming from your two eyes, the two separate images, combines them together in such a way as to make it look three-dimensional. If you only ever had one eye and you look, everything looks two-dimensional. Everything looks flat because you can't get a sense of perspective. You only have a view from one angle, so it looks like you're looking at a computer screen or a piece of paper or something. But the fact that you have two eyes that are separated a little bit, you get two slightly different angles of every object, and your brain does all the computing power for you and combines those images in such a way as to create a three-dimensional image of what you're actually looking at. Now, what 3D movies do is they try to reproduce this, because usually what's going on is you have a camera, it's got one lens, one eye, and it's looking at what's going on, and it basically records that information. And so when you watch a movie, it's on a flat screen. It just looks like what you're used to. Now, your brain is still looking at this flat screen, and giving you a sense of the fact that there's 3 dimensions there. But, you know, it looks flat. Just like when you look at a drawing, it's flat, even though some people can do a 3-dimension, you know, you draw a little cube, for instance, like this. This looks like it's 3D. Oh my God, look how horrible this is. This looks semi 3D, but it's actually flat. So our brain can trick us in some ways to make it look sort of 3-dimensional, but it's not really. So what people wanted to do was find a way to reproduce this effect of generating a 3-dimensional view by having 2 slightly offset images and combining them together. Now, here's the problem. If you've ever been to a 3D movie and you didn't wear the glasses, it looks horrible. It's literally 2 movies on top of each other, slightly off. So everything looks blurry as heck. So how then does wearing these glasses help? How does it combine the images for you to make it look 3-dimensional? What they do is when they're recording a movie, this is kind of a more simplified version, but it's basically the effect. When they record a movie, they have 2 different cameras or 2 lenses, and those lenses are separated by a little bit, just like your eyes would be separated by a little bit. And so everything it's recording, it's got 2 separate images from 2 slightly different angles being recorded. And then when you go to the theater, the projection plays those 2 images at the same time onto the screen. And that's why if you don't wear the glasses, it looks blurry, because your 2 eyes are looking at the screen and there's 2 images there. Well, your brain doesn't have the ability to kind of do the calculations for you to make it look nice. It's looking at something with 2 pictures on top of each other. So what they want to do is reproduce the effect of each eye being a separate image. So when they play the 2 images, let's say the left camera and the right camera, the left camera, when it sends the image out, it's polarized vertically. All the light from that camera or the projection of that camera's image is polarized vertically. And then the right camera, the second one, all the light coming from it will be polarized horizontally. Now, again, your eyes can't see polarization, so it doesn't matter. When you're looking at the screen, you see the 2 images like normal. However, the glasses, the left lens, is a polarizing filter, which only allows light, which is polarized upwards or vertically, to get through. And it blocks all the light, which is horizontally polarized. So if you put these glasses on and you close your right eye and you're only looking with your left, you only see 1 image, because the second image, which is polarized horizontally, is completely blocked by that lens. And then, of course, the other lens is exactly the opposite. The right lens is polarized horizontally. Thus, it only allows light that's coming in polarized horizontally to go through, and it blocks all the light which is vertically polarized. So if you close your left eye and you look at it, you see the other image, but the first image is now gone because it's blocked. So when you open both eyes, your left eye is seeing one of the images, your right eye is seeing the other image. Well, that's exactly what happens in real life. When you go around and you look at things and you open your eyes, your left eye sees something, your right eye sees something slightly different. That information goes to your brain does a calculation and tells you what you're seeing. So with these glasses, it reproduces the effect. There's 2 images playing at the same time, polarized in opposite directions. The left eye can only see one of them. The right eye can only see the other. Your brain thinks you're seeing with no glasses on. And so it does the calculations and it looks 3-dimensional. That's how 3D movies work. It uses a polarizing effect to allow this to occur. Now, technically, this is called the passive 3D movie way of doing it. There's also an active. They have more fancy 3D goggles that require batteries and electronics. And it does it slightly different, where it changes the polarizing filter in both lenses simultaneously really, really rapidly. That's a different effect, but it still uses polarization exactly the same way. But the one I'm using or talking about, the passive version, is a little easier to see and understand. It reproduces the way your eyes see, but it uses polarization to trick your eyes with the use of these glasses. You need the glasses for it to work. So this is something we use. This is something that's useful. And oh, by the way, there's another thing polarization is used for. It turns out, interestingly, that when you send polarized light through certain materials, the polarization angle, the direction the electric field is oscillating, the polarization, can rotate a little bit. So if light coming in was initially vertical, and you send it through a particular material and it comes out, it may now not be vertical. It may have been rotated a little bit by 30 degrees or 40 degrees or something like that. And so it turns out that sugar syrup type companies, when they want to create their syrup, they want to know how sweet the syrup is. How concentrated is the sugar in this syrup? And they don't want to have to taste it, of course. They want to be able to scientifically determine it without having to interfere. And the sugar syrup is one of these materials that has this rotational effect. When polarized light travels through a sugar syrup, it rotates the polarization angle of the light. And of course, the more concentrated the sugar is in the syrup, the faster it rotates it. So if you have, for instance, this vat of sugar syrup, here it is, and you send light through and you get light out, you test the light over here. Well, if you knew the light was initially vertically, and of course, you know the thickness, you know, what is this distance the light is going to travel, how fast does it travel, how long does it take to get through, all of that stuff. And you say, okay, well, for a certain concentration, if it's concentrated at 80% sugar, then it should rotate the polarization by 1 degree per nanosecond or something. And so you can do, there's calculations to do, but basically at the end of the day, when the light gets through the sugar syrup, it's now polarized this way at some angle. You say, the fact that the polarization rotated this much tells me the sugar concentration. And so they send light through, they see the new light that comes out. How is it polarized? Was it rotated enough? If it's not rotated enough, it means the syrup is not sweet enough. So they add more sugar until they get the right amount of rotation, and then they know the concentration of the sugar in the syrup. So again, a different way, completely different way, that the polarization characteristic is useful in industry, for instance. So it's an important effect, thus we should know about it. Now, what is it we're going to do, of course, because we're not in industry, we're not making corn syrup or anything like that. What we want to do is be able to predict. We want to say, given light polarized in a certain direction, it's going to travel through a certain filter. The filter is polarized in a certain direction too. And you want to know how much of the light will be blocked by this filter. In order to do it, we used what's called the Law of Malice. Now, it sounds like an evil equation, but it's not spelled the same way. It's not, unfortunately, it's not malice, like evil. It's malice, M-A-L-U-S, a person's name. The Law of Malice. And this is the equation or the law that we will use to determine how much light, and when I say how much light, what I mean specifically is called the intensity, the brightness, let's say. the intensity of the light which makes it through a polarizing filter. An equation goes like this. The intensity that makes it through, that's what I is, intensity, is whatever the starting intensity was. Of course, it should depend on how bright the light was originally, times cosine squared of theta. That's it. Very easy. I is intensity. I naught is initial intensity. And theta is the important one. That is the difference between the polarization of the light and the filter. Okay. What does this mean? What does this look like? Typical problem goes like this. Light initially polarized vertically, and this is the symbology I use. That's vertically polarized light. And for all of the problems we're going to do, I'm just going to say the initial intensity is just I naught. I'm not going to give it a number. Okay. If you're actually doing this in real life with real experiments, you would know an actual value for the initial intensity of light. It's a certain brightness. But in this case, we're just going to use I naught and leave it as a variable. Just leave it as I naught. It's easier. So I naught, the initial intensity of light, and that light is initially polarized upwards. It's going to be running into a filter. There's my filter. And let's say this filter is polarized in this direction. This is the symbol I use for a filter polarized at an angle, and I call the angle, let's say in this case, 30 degrees. Okay, that's going to be the symbols I use. So if the filter is polarized vertically, I just have a vertical arrow. If it's horizontal, I have a horizontal arrow. And if it's at some angle, then I'll always have this kind of symbol. That's an angle symbol. And I'll put, 45 degrees or whatever the angle is for the filter. All right, so there's my problem. Vertically polarized light of an initial intensity I naught is incident upon a filter whose polarizing angle is 30 degrees. The question is, how much light makes it through? What is the intensity of light that makes it through? Well, in order to do this, we use the law of malice. I, the intensity that makes it through, is I naught, the initial intensity, times cosine squared of theta. So I naught, we leave it as I naught. We don't know the number. We just leave this as a variable, always. Cosine squared. Now the theta is the important piece here. This is the critical piece, and this is where most things go wrong. When you put theta in, you don't just look at what the angle is. Okay, so there's an angle on top of that polarizing filter, it says 30 degrees, but that doesn't mean theta is 30 degrees. Because if we look at what the equation says, theta is the difference between the polarization of the light and the polarization of the filter. Well, the filter's at 30, fine, but the light's not at 30. The light's actually at 90. It's vertically polarized. So when I go to do theta, I need the difference between these. I'm at 90. I'm trying to get to 30. So 90 minus 30 is 60 degrees. And 60 is the theta I need for this problem. That's an important thing to know, because a lot of people make this mistake. When you go and you're rushing through and you don't really know how to use this equation, you see theta and there's an angle staring you at the face, you want to put the angle in for theta, but that's not the angle you put. Theta means what is the angle of the light initially? The light's coming in, what's his angle? And then the angle of the polarizer, what's his angle? Take the difference between those two angles, and that's what you write down for theta. In this case, it happens to be 60 degrees, 90 minus 30. Here's another thing to know. This is a mathematical truism, something you should know forever, especially if you're in physics and engineering, because it's useful. I remember I learned it in math class, but I didn't really care about it. It was kind of whatever. And then I got to, at UNO, I was a graduate student at UNO, and they have a series of classes, 5 semesters worth, in what's called Fourier transforms. It's a signal processing, data processing type series of classes. And so I did all 5 semesters of Fourier analysis, Fourier transforms. And one of the things I learned in the very first semester is that this fact is useful when you do things like integrals in calculus, because there's a lot of integration when you get to some of these higher level physics classes. The thing that's useful is to know this: trig functions. So sine and cosine. Cosine is even. It's an even function. And what that means is the cosine of theta is the same as the cosine of minus theta. So that is to say, the cosine of 2 pi is the same as the cosine of minus 2 pi. Okay. Sine, the sine function, is an odd function. What does this mean? This means that the sine of theta is equal to minus the sine of minus theta. It's odd. That means if you put the negative angle, then you get a negative answer from what it would have been if it was a positive angle. So the sine of pi or minus the sine of pi is the same as sine of minus pi, is one way of saying it. So cosine is even. What that means is when you plug an angle into the cosine, you could either plug it in as a positive number or a negative number. It doesn't matter. With the sine function, it does matter, because if you put a negative angle, you get a negative answer. Positive angle gives you the positive answer. Now, what I mean, I don't mean always. What I mean is, if the sine of the angle was positive, then sine of minus that angle is negative. But vice versa is true as well. If sine of the angle was negative, then sine of minus that angle would be positive. They're the opposites. Now, I say that because when you go plug theta in here, there's going to come a time where these angles are such that when you take the difference, you get a negative number. So for instance, if the original intensity were 0 degrees and the polarizer is at 30, 0 minus 30 is negative 30. And so I get questions a lot saying, should I put the number as negative 30 or 30? And the answer is, it doesn't matter. They're the same thing. So my suggestion to you is, when you take the difference of these angles, whatever answer you get, make it positive. Just forget about the negative. Always positive angle in there, just because it doesn't matter. If this were sine, it would matter, but it's cosine. Now, not only that, on top of that is cosine squared. So even if it did matter, you're squaring it anyway, so it's going to be positive anyway. But this is a little thing you should have in the back of your mind, that in 2, 3, 4 years may come back up and be useful in some way. Like I said, in advanced classes, when you're doing some of these integrals and the integral looks messy and you're like, oh my God, I don't want to do this calculus stuff. And then you see, oh, the sine function is odd. Well, because this is an odd function over symmetric limits, that means no matter what this is, it's equal to 0. I know immediately it's equal to 0. I don't even have to work it out. So little things like that pop up and you're like, oh my God, thank God I know this. It makes the answer easy. Or for cosine, I have an even function over symmetric limits, change the limits to 0 to whatever and multiply by 2. Very easy. Here, I only say it just to let you know that when you go to use the law of malice and you plug this angle in here, because it's cosine, you can just plug it in as a positive angle. You don't have to make it negative if when you take the difference, it becomes negative. Anyway, class has just got over. Let me give you the answer. Cosine of 60 squared gives me 1/4 or 0.25 I naught. And that's the answer. Leave I naught as just a variable. We don't know what the number is and we don't care. Cosine squared of 60. By the way, if you're curious what cosine squared means, because I remember the very first time I was in trigonometry and I saw something like cosine squared, I didn't know if it meant cosine of 60. So it's literally cosine times, cosine of cosine is cosine squared. Or is it cosine of 60 squared? Or is it cosine of 60 whole thing squared? Which one of these? Turns out it's this one. Cosine squared 60 is the same as cosine of 60 squared. That's what it means. They don't write it like this because it can be confusing whether the square is on the 60 or is it on the whole number itself. So they write it like this. Cosine squared 60 means it's cosine of 60 times cosine of 60. Or cosine of 60, that number squared. Okay. All right, so any questions about this law of malice so far? All right, well, next time, Thursday, we will do a whole bunch of examples on this. Make sure we understand it. And by the way, Thursday will be the last lecture day we need. So I think this will be the last topic we'll worry about, making sure we understand polarization well. Tuesday of next week is our last class, and that's when we'll do a final exam review. We'll talk about what will be on the final and all that. Of course, final's cumulative, so you already know. But Tuesday will be the final exam review. This Thursday, we'll be finishing up, reviewing law of malice, reviewing polarization, and doing a bunch of examples to make sure we understand how to do these calculations. Because like I said, this is the basic. What we're going to do is add in more filters. What if we have a second filter or a third filter? How do we accommodate more than one filter into this equation? That's what we'll do next time. So if you don't have any questions, you are free to go, and I will see you on Thursday.